Mhm. Hello, everybody. This is Professor Ma, and this is the summaries on all the derivatives that we went through. Let's start out with the simple derivatives. Uh, we start out with the simple derivatives, some functions, input, output, and in particular, we use x as the input and y as the output. And we also call, say this is the independent variable. Okay, and this is the dependent, it depends on the input, dependent variable. Okay, and the simple derivatives is we have output y depends on input x, and then we take the derivative with respect to x, and the most important rules in this derivatives process, the differentiation process is the chain rule. And so we finish with these as the answers. And notice I'm using the notation prime. And this prime notation is, of course, in this case, dx. I'm taking, since x is the input variable, so the prime is always taken with respect to the independent or the input variable. So in a problem that's not in the letter x, y, later on, we'll have problems in letters u and v. And there's no clear indications who's the input, who's the output variable, unless the problem tell you to view the problems as using one of the variable as input, the other one as output. So when the derivative taken, you have to follow that input variable. Okay, so we'll get that. You look at it. You'll see. Okay, and second things I want to say about this y prime. So it's ddx. So in particular, what I find out, what I calculate is this dy dx, which is the same as y prime. And bear in mind, dy dx is the ratios of the output to the input. So if I fluctuate the input by delta x, what's the output in relation to the ratio of the corresponding output to the delta x. So that is what this dy dx is. So it's a small ratio. So in this way, later on, we can make sense what dx dy is. Since it's a ratio, I can turn around, right? I can flip the fractions. Now, it's more on chain rule. Suppose now the x is the input variable and the y is a function in x, in particular is cosine x, and u is the output. So I want to find du dx. Okay, so I'm going to find u prime. Okay. Here, notice again, because we designate the x as the input variables, therefore the derivatives will be automatically its respect to the dx. So when I take derivative with respect to dx, then derivative x squared is just 2x. But derivative of y, ey, I have to use chain rule because y is a formula in x. So that's on the back part, the chain rule comes in. Of course, y, I know what it is. I can plug it back in if I want to figure out what the corresponding answer is. The point about this exercise is, suppose I don't know what y is, it's vague. Then the calculation I can carry out up to this point is correct. This up to this point, I don't have to know what y, the formula y is. I can leave it in this form, u prime is equal to that. And this we call implicit form. Okay, so now come to implicit differentiation. So implicit differentiation now in the following example, I'm going to use two letters u and v. And so there's no preconception who plays a role of x, who plays a role of y. And whereupon I can designate and say, oh, look at this as a function u in terms of v or the other way around. Okay. So here, I'm treating the letter V plays a role of X as an input variable. And I want to know the U is derivative of U with respect to dV, and in other words, I want to know what du dV. Okay, du dV is, except what the notation I'm going to use again is a prime. And if you have to keep in mind when you read these prime, since it's in U and V, you have to know what this derivative is taken with respect to which letters, and you have to go back and check, oh, with respect to V. Hence, when I take derivative of VQ, that's just 3V squared. But if I take derivative of U, I have to invoke chain rule. U is a function in V. So if I take derivative of V, that's what's on the left-hand side. On the right-hand side is a product rule. But derivative of V, in this prime notation, everything is taking the derivative with respect to V, so V prime is 1, dV dV. So I get that, then I can solve for U prime. So bear in mind, U prime is du dV, because this is what we started out with the assumption using V as the X. Okay, and so that's what du dV is. And that's the approximate, the change ratio of U to, you change the input V slightly. Do it the other way around. Now view the equations, use U as the input, V as the output. So now I'm taking derivative with respect to U, and that's what this prime. So in this context, the prime over here is d du. So when I take this derivative, that's just for U. I don't need U prime. U prime is 1 because du is 1. But this, I need to use chain rule. That would be 3V squared times dV du, because V is a function in U, or simply put V prime. In other words, I have these. And now I'll solve for V prime, dV du. Okay. And notice, if you compare this with the last answers in A, it's a reciprocal of the other answers. And of course, du dV, if you view it as fractions, as a ratio, I can turn around as dV du, and it's just reciprocal. Therefore, the pairs of derivative, depending on who you use input, who you use as output, you get these derivatives implicitly, which are the reciprocal of each other. And this is true is because when you flip them around, you're talking about inverse functions. Viewing U as a formula in V or V as a formula in U, then they form an inverse pair. On the inverse pair of function, the graphs is symmetric with respect to the x-axis. So if I have a graph over here, that its inverse will go like that. The symmetric. So if I have a point that the slope is it's something m, then at a corresponding point over the slope on the other side, it's 1 divided. These two slopes are reciprocal of each other. If one of them is 2, the other one is 1/2. Okay, and that came out of these two derivatives with respect to each other implicit way, the implicit differentiation, they are the reciprocal. Okay, geometry. Oh, sorry. There's a related rates derivatives. This is where we have all the variables actually a formula in T, specified. It's not given as a formula in T, but it just assume everything change according to times, and then we use chain rule to being able to calculate the derivatives of one of the letters, okay, X, Y, or Z, you name it, you pick one. We can calculate that particular letter's change with respect to time in terms of all the other letters here. So now everything is in formula in T, meaning when I do the algebra, I have to use chain rule for both letters U and V, because they are actually in terms of T. So, okay. Now, so this derivative is respect to T. T is the independent variable, the input variable. So I'm taking derivative with respect to T. So the from part with respect to T, I have to use du dt and the v and dv dt. Product rules, u prime du dt times v, 2 times u dv dt. Okay. Now, in particular, it tells us du dt. Oh, what do we wish to find in here? These are the relationship between u and v and the du dt, dv dt, all mixed up together. In particular, if I give you enough information of 3 of the letters, you can figure out the fourth one. Okay, so well, usually we figure out the du dt or dv dt. So in this case, we want to find out dv dt. So there will be a lot of information given about u and v and du dt. So I can plug all these numbers in these equations, so I can figure out what v prime is. In other words, we're going to calculate v prime, and the other places u and u prime, and they're all going to finish, and the v, they're all going to fill in with numbers. And you put them in, and then you get v prime is equal to 6. Okay. So we'll say, okay, that's dv dt is 6. Okay. That's the geometry. Okay, let's come talk about geometries. So the other, so we just finished with all the algebra, different way of viewing formulas taking derivatives. Now, what does the derivatives tells us? Okay, here, so here is the picture. Derivative, of course, gives the slope of the tangent line at that point. So in particular, let's start with looking at derivative 0. Derivative 0 means tangent line is horizontal. What could the picture look like? A curve where you can balance a, think of a curve floating, in somewhere. I think of a place you can put a ball on the curve, and the ball is not going, it's not rolling downhill or uphill. It's stable. Okay, so the ball could be, I won't say stable, it's stationary. Okay, so on top of on the bottom, or on the shoulder points, these are the only 4 possible configurations. If I know the derivative at a location is 0, then if I take my microscope, look at that, zoom up on the pictures at that point, then it has to look like that. One of these at that point. What happens if the derivative is positive? Well, then just the other 4 cases was horizontal, just tilt it until each tangent instead of horizontal now tilt it, so the derivative is positive. So tilt the other way. Yeah. Derivative negative means tilts the other way. So in other words, if I know the sign of the derivative, these 12 pictures, this derivative 0, derivative positive, derivative negative, it's one of these pictures. Okay. So here is again equations which is in terms of u and letter u and v, and now we want you to specify that we're going to view u as the input or independent variable, v as a functions in u. In other words, we're going to treat x as the u as the x. Okay, if you want to think of that. When I take the derivative, therefore, this, I need to take the, I don't need chain rule, the derivative of this respect to u, du is for u. But for vq, I need derivatives, v prime. Okay, derivative of 2v is 2v prime, dv du. And I solve for v prime, dv du, and then plug in the points, and we get v prime is 0. So what does that mean? What does that mean? What does this mean? It means, well, first of all, we have a situation where u is viewed as the x, v is viewed as a y, and we have a point 0 minus 1, which is on the curve, okay? So the curve might be, I don't know what it is, but it pass through here, and I don't know what it does. It does something. And now the question is asking you to zoom in at 0, 1, and take a look at it. Tell me what the curve looks like. We have that it is dv du at that point 0. So say, therefore, the tangent line at that point is flat. Okay, and there's only 4 possibility. And which possibility of that is? Well, take the second derivative. Okay, if I take the second derivatives and I plug in the point, I find out the second derivative is positive. Aha. Therefore, the only possibility is a minimum. Okay, so this is, in other words, this allows us to be able to focusing around a neighborhood of each point, and I can have a better sense of the geometry around individual points. So this is the geometry, okay, and this is the summary of the derivatives we want. Okay, bye-bye. Stop here.